Music and wine chi-square test. Market researchers know the background music can influence the mood and purchasing behavior of customers. One study in a supermarket in Northern Ireland compared three treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of bottles of French, Italian, and other wine purchased. Here's a two-way table that summarizes the data. We're given the data for the type of wine sold and the type of music played in the background. Analyzing the problem, we see that the type of music is the explanatory variable. It is used to predict the number of bottles of wine sold. So the type of wine is the response variable. For the conditional distribution of the response variable for each value of the explanatory variable, we would compute the column percentages where we take the number in each cell divided by the total in the corresponding column. Again, because the value in the explanatory variables are the headers of each column. Part A is done for us. We are given the conditional distributions. Using this distribution, we can say that French wine tends to perform better than Italian wine. The percentage or the number of bottles of Italian wine sold for each of the background music played are small compared to the French wine and other wine. Part B. Perform the hypothesis test to determine if the proportion of each wine type sold are the same in all three populations. This is the C to C row type classification where the explanatory variable is the type of music played in the background, which is categorical, and the response variable is the type of wine sold, which is also a categorical variable. For the C to C row type classification, the hypothesis test that we would need to perform is called the chi-square test. The null hypothesis is the statement of indifference. And so the null hypothesis in this case is the assumption that the proportion are the same for all three types of wine. However, for the chi-square test, the hypotheses are stated in words. For the null hypothesis, the type of wine bottle purchased and the background music played are independent. That is usually how the null hypothesis for the chi-square test is phrased. We would list both variables and we state that, or we assume that they are independent. The alternative hypothesis is that they are not independent. This is the standard hypothesis in the hypothesis test, the null and the alternative hypothesis. This is the first step in a hypothesis test. The second step is to collect the evidence which we have in the form of the data, and we need to summarize this in the form of a test statistics. We would need to compute what we call the chi-square test statistic in this case. The chi-square test statistics is computed using the sum of all cells of the observed value minus the expected value squared divided by the expected value. That is, for each cell in the table, we would need to compute the expected value. We take the observed minus the expected, take the quantity squared and divide it by the expected value. This will give us a number in each cell, and we would add all of these corresponding numbers to get the chi-square test statistics. Each of the numbers in the sum that we compute in this case is called a contributor to the chi-square test statistics. The observed values should be given in the table already. The expected value is computed using the formula n times the probability of A, B. Each of the number in the cells is a compounded event A and B. For example, 30 represent the event A, French wine, and B, none music play in the background. 1 is a compound event for A, Italian wine, and B, French accordion music. The expected value is therefore the probability times the grand total. But since we assume that event A and B are independent in the null hypothesis, we always assume that the null hypothesis is true in a hypothesis test by the probability rule. The probability of AB is the probability of A times the probability of B. And so for the cell with the number 30, we would need to take n, which is 243, the probability of A, the probability that French wine bottles are sold is 99 French wine bottle total divided by 243 total bottles times the probability of B, which is the probability that no music play in the background, 84 divided by 243. We canceled out 243 to end up with only 99 times 84 divided by 243. And so the shortcut here is to compute the expected value for each cell. We don't even use the number in the cell. We take the product of the corresponding total in the row and the column of that cell divided by the grand total. So for cell 30, the observed value is 30 and the expected value is 99 times 84 divided by 243. And that will give us 34.22. Again, this is the expected value for that corresponding cell. Similarly, for cells with number 39, the observed value is given 39 and the expected value is 99 times 75. Again, the total in the corresponding row and column, we multiply them and then divided by 243. If we take 99 times 75 divided by 243, we will get 30.56. For the cells 30, this time, the total in the corresponding row is 99 and the total in the corresponding column is 84. So 99 times 84 divided by 243 is 34.32. And so we have the expected value for each of the cells in the first row. Similarly, for the cell with number 11, the observed value is 11 and the expected value is 84 times 31 divided by 243, and we'll get 10.72. With the cell with number 1, the observed value is 1 and the expected value is 31 times 75 divided by 243. We will get 9.57. Similarly, 10.72 39.06, 34.88, and again, lastly, for the last cell with the number 35, the observed value is 35 and the expected value is 84 times 113 divided by 243. That is 39.06. Once again, to obtain this expected value, for example, with the cell with number 1, we would take the product of the total in the corresponding row and column. In this case, 31 times 75 divided by the grand total, 243. And that is how we get 9.57. This is how we read the observed and the expected value. For example, for this cell, we observe from the data given that 30 bottles are sold. However, we expected that 34.22 bottles should be sold. Similarly, for this cell with number 1, in actuality, they sold 1 bottle, or the observed value is 1, but we expected that they should have sold 9.57 bottles. Now that we have the expected value, we can compute the contributor for each cell. For a cell with number 30, the contributor is the observed value minus the expected values, square this, and divided by the expected value, 34.22. If we compute this, we would get 0.52. Again, this is called a contributor to the chi-square test statistics. There are 9 numbers in the table. There are 9 cells. We would end up with 9 contributors. This is one of the 9 contributors that contribute to the chi-square test statistics. If we perform similar computation, we will get 0.52 for the first cell with 30. For the cell with number 11 with the expected value of 10.72, the contributors will be 11 minus 10.72, the quantity squared, divided by 10.72, and we will get 0.0073. Let's round everything to 4 decimal places because the number are quite small here. For the cell with the observed value of 43, the contributor will always be observed minus the expected squared divided by the expected. And so in this case, we would take 43 minus 39.06, take the quantity squared, divided by 39.06, and we will get 0.3974. Take 39 minus 30.56, the quantity squared, divided by 30.56. We get the contributor 2.3309. Performing similar computation to get 7.6745, 0.0004. This is why we round it to 4 decimal places, because the numbers is again small. 0.5204, 6.3954, and lastly 0.4220. To get 0.4220, again, we take the observed minus the expected, take the quantity squared, divided by the expected value. There are 9 contributors. We add all of these numbers up to get the chi-square test statistics. That is, take 0.5204 plus 0.0073 plus 0.3974 plus 2.3309 plus 7.6745 plus 0.0004 plus 0.5204 plus 6.3954 plus 0.4220 to get the chi-square test statistics. If we add them all up, we will get 18.27. The degree of freedom for the chi-square test is the number of row minus 1 times the number of column minus 1. In this case, there are 3 rows, so R equals 1, and there are 3 columns, so C minus 1. This is 2 times 2, which is 4. With the chi-square test statistic of 18.27, with the degree of freedom equals 4, we look up using either the table or the chi-square distribution to get the p-value of 0.0011. Once we get this p-value, we can conclude that this is less than the standard alpha. Alpha is not given here, so we would need to use 0.05. Because the p-value is less than alpha, the significant level, we would reject the null hypothesis. If we reject the null hypothesis, then we would say that the type of wine purchased and background music played are not independent. Since we reject the null hypothesis, we support the alternative hypothesis. We wrote the first 2 steps of the hypothesis test. Make sure to include the next 2 steps as well. They are the p-value, reject the null hypothesis, and we would write one complete sentence for the conclusion. Since the p-value is small, we have strong evidence against the null hypothesis. That is why we reject it. We then conclude that the type of wine purchased and the background music are not independent. That is, the number of bottles of wine sold, the type of wine sold depends on the background music played. Observe that the hypothesis test does not tell us how the proportions are related. That is why we would need the conditional percentage from Part A. However, the contributors tell us something. The largest contributor to the test statistics is 7.67, and it corresponds to the cell with number 1. In this cell, the actual number of bottles of wine sold is 1, when we expected that 9.57 bottles would have sold. This indicates that Italian wine underperformed when French music is played in the background. We now end this video with the instruction on how to obtain the p-value with the computed chi-square test statistic that we obtained earlier. Using Desmo.com chi-square distribution, we need to specify the degree of freedom, in this case 4, and we would need to enter the chi-square test statistic that we computed. It was 18.27, and the calculator provide the p-value 0.00109, which we rounded to 0.0011. With the chi-square test statistic with degree of 4 and more, the distribution has a right skewed shape. This is not symmetric. This distribution is skewed to the right. Desmo's calculator also has a feature that allows us to perform the test without computing the expected value by hand. With this calculator, we use the three columns and we enter the data. These are the data provided in the table. The calculator will do the rest when we enter these numbers. There are 9 cells here. If we scroll down, we see that the chi-square test is 18.28 and the p-value is 0.0011. Now the numbers are slightly different than what we obtained earlier. This calculator provides a chi-square test of 18.279, which we rounded to 18.28. But earlier, the chi-square test that we computed was 18.27. That is fine. This is simply because of the round-off error. Remember that the observed and the expected value, the difference, can influence these decimal numbers. Regardless, we get similar chi-square test statistics and the p-value. But in this case, we only need to enter the values from the provided table.